Once again, a very good morning to all. Welcome to the third day of the 5-day e-workshop on recent trends in operation and planning of distribution system and microgrids. I welcome Dr. Siqi for his second session in the workshop on the topic Intelligent Operation of Modern Power Systems. I now request Dr. Siqi to deliver the session. I request the participants to kindly post your queries in the chat box. Over to you, sir.
Okay, thank you very much, Jisma. Can you all hear me?
Yes, sir. Yes.
Okay, great. Yeah. So let's make a start. So is the slide sharing okay for you?
Yes, sir.
Okay, great. Yeah. So so thank you everyone for your attending. So today my presentation topic is intelligent operation of modern power systems. So before I get started, I just want to acknowledge some researchers in my group. So today's presentation is part of their work. Okay, so before I go into the the contents, I just want to brief some transformation or the development of the power industry in the modern society. So we talk about the 4D transformation here. So they are the decarbonization, digitization, decentralization, and deregulation. And this 4D actually are happening, in all levels of the power industry. For example, for the generation, for the production of the electricity, right? So we are experiencing the decarbonization, right? So we are phasing out the traditional conventional thermal power plants, and then we are using more and more the renewable energies, and also to make the grid and operation smarter, right? We are trying to digitizing the power grid and using more and more sensors, right? The IoT technology, right? To make the operation more intelligent. And also we are experiencing the decentralization. So it happened both to the generation side and also the demand side. So for the generation side, as I just explained, we are using more and more renewable energies. So some of them actually are integrated in a distributed way. And we have seen a lot of embedded generation, right, connect to the distribution network as well as the microgrid. And for the demand side, actually, we have seen so-called the prosumer, right, the producer plus the consumer emerging. So they can actually to supply to the grid by using their, for example, rooftop PV panel or even the wind turbines. So this is a decentralization. And also based on this kind of trend, we have seen quite a lot of different control strategies, right, to achieve this decentralization. And deregulation is talking more about the market perspective. So I think yesterday some speakers actually was talking about the some transformation, from the vertically integrated market to the, for example, the wholesale competition market, or some other new market types. So this deregulation actually is happening with like a dynamic, a continuous basis. So in order to achieve this 4D transformation, so there are some enabling technologies, for example, like artificial intelligence, right? This is the one actually we're gonna focusing today. And also we have seen like the blockchain, right, to facilitate the peer-to-peer trading, right, transactive energy, and clean energy I've just mentioned, right, to connect more renewable energy, cloud computing, right, to since we have sensors, we collect a lot of data, right? And then we try to use cloud computing, a resource to actually to process the data. And digital twins actually is something quite new as well. I think it's starting from probably early this century, um, and it was introduced to the power industry probably after 2010. So we are using some high performance simulator to achieve the digital twins functions. And distributed energy resources is more talking about the renewable energy or energy storage, right? Like, or the electrical vehicle, right? Connect to the grid, energy conservation, right? And ICT, Internet of Things, and virtual reality. So you will find actually quite many of these technologies, they are part of the Industry 4.0, right? So which significantly facilitate the transformation of the power industry. So for more details, you can refer to this web link. So now I just want to probably just brief the history of the AI evolution. So and also look at the AI applications in power system. So as you might know, the AI technology actually experienced some ups and downs, right? So it was started, or it was initially developed in the early 1940s, and then it experienced some winter season for the AI in the 1970s, 80s. But recently, based on the development of the deep learning, especially for some new deep learning technologies, the AI become more and more popular and used in a lot of industries and also the different sectors, departments. So, but this is not the focus of today. So today I just want to more focusing on the AI application in power system. So when we're talking about the AI application in power system, there are quite many aspects. But I should say, although it has been used in many areas, the application actually is still in a very initial stage. So, for instance, like the dynamic security assessment or situation awareness, I'm going to talk about in a moment. So they are still in a very early stage. And also here you can see there are some other applications like the prognostic health management of the power equipment, and the fault detection, anomaly detection, and predictive maintenance, and power quality assessment, intelligent overhead line inspection, as well as some intelligent control strategy for grid operation. So today I'm gonna focusing on some these highlighted applications, okay, including the situation awareness, predictive maintenance, and intelligent control for grid operation. So as we all know, as a system operator, what we try to achieve, there are three objectives or three targets. Okay, the first one is security, right? The second one is reliability. The third one is to be more cost effective, right? So so our first motivation is to improve the reliability of the power system operation. So in order to improve the the reliability of the power system operation, so the first step is you need to enhance the reliability of the power equipment. But in the modern power grid, actually, it actually poses quite severe threats to the system operator to maintain the system reliability. The reason is that we introduce a lot of power electronic components, right, to the power grid. So their characteristics could be quite different from the conventional power equipment. And also we actually introduce quite amount of the communication equipment to the grid as well, in order to make the operation more intelligent. So with all of these components connect to the grid, it makes the power equipment more vulnerable, and also make the anomaly more invisible. So so it is actually provide a lot of challenges to us in terms of the anomaly detection and also the predictive maintenance. So here I would like to first introduce some basic concepts or development of the maintenance of the power equipment. So we actually experience three stages, okay, for the maintenance. The first stage is so-called the breakdown or corrective maintenance. We call it CM here. So the concept of this maintenance is we only repair the power equipment after failure. Okay. So for this maintenance, actually the reliability is quite low, right? Because you only repair when you find the equipment or the devices are broken, out of service. It also actually give us a huge risk, right? Because so once you have a power equipment down, right, it could lead to some further tripping of the transmission line or transformer or some other equipment, right? So it will cause cascade events to the grid. So it's not that favorable. The second stage actually is the so-called preventive maintenance. So the preventive maintenance, it means we repair the equipment in a periodical manner. So for example, we replace the cable joint, right? Or we actually we replace the oil of the transformer every year, right? So so this is like an insufficient or excessive maintenance. We don't know if the equipment is really in an unhealthy condition, or it's it's not that cost effective in a way. So that's why we introduced this. The third stage is called condition-based maintenance. So in November 2002, the U.S. The Secretary of Defense for Logistics and Material Readiness released a policy called the Condition-Based Maintenance Plus. So this concept actually represents an effort to shift the unscheduled corrective equipment maintenance of the new and legacy systems to preventive and predictive approaches that schedule maintenance based on the evidence of need. So this type of maintenance is based on the condition monitoring, the health monitoring of the equipment. Today I would like to introduce some of our work on this condition-based maintenance. So we call it predictive maintenance. Okay, here. So this predictive maintenance actually is based on the data analytics, and it is and one type of a proactive maintenance. So when we talk about the predictive maintenance, one of the most critical challenge is the data. So as you might know, for some components, power components, okay, in the power system, like the cables or like the switch gear, right? We don't experience a lot of broke down, or we don't experience a lot of very frequent outage for those equipment. So that is the reason we don't have many data, right, for this equipment. So it normally take years or even decades to accumulate the data for this equipment. But on the other hand, for most of the AI algorithms, especially for deep learning, they actually are very data demanding. So they need a lot of data to train the model, right, in order to get an accurate result. So that's kind of a challenge for us to perform this predictive maintenance. So based on this context, we propose a so-called predictive and proactive maintenance strategy with a novel combination of model-based and data-driven approaches. So, which means this solution is not a purely data-driven approach. It is a combination of model-based and data-driven approaches. We also call this one as a fusion methodology. So the advantage of introducing this model-based approaches or proactive maintenance, the first one is we can solve the data deficiency problem, right? The second one, actually, it gives us more in-depth understanding on the physical failure, the mechanisms of this equipment problem. So the proactive maintenance here is based on the degradation and the failure mechanism, and the predictive maintenance is based on the deep learning techniques. So we are using the long short-term memory and the RN techniques to predict. So first we look at the proactive maintenance, which is based on the model we proposed a technique. So for this this model-based predictor, actually we are looking at many two different types of failure. So so this work actually is the collaboration with the high-speed rail of China. So we are mainly look at the switch gear, okay, of the traction power supply system. So for the switch gear, actually it's experienced a very sudden change of of the demand, the load. So there are mainly two different types of failure. So one is called the heart failure. Okay, this heart failure could be caused by the magnitude of the the power demand exceeds certain threshold. Okay, so for example like this one, or it could be caused by too frequent the load changing. Okay, so if this the two load changing in a very short time scale, it might cause the equipment failure as well. So these two different cases, we actually treat them as the heart failure. And there are also some failures related to the so-called soft failure. And so this soft failure actually is mainly due to the aging problem. Okay, so it could be it could be due to the the equipment is is too old, or it could be due to some accumulation of heart failure, and this this heart failure will accelerate the aging of the equipment, so it will cause the soft failure. So based on the the characteristic of the heart failure and the soft failure, we establish some models for these failures. We're using some the Poisson process, as well as some homogeneous the Poisson distributions to characterize these failures. And then based on this probabilistic modeling, then we can generate the the breakdown time of the equipment. So here I just list an example for the remaining useful life of the switchgear based on the sample generator. So there are totally 10 failure parameters for these models. So if you are interested, you could have a look at the paper below. And the second predictor is so-called the maintenance predictor. So we are using the ASTM and RNN based maintenance predictor. And for the data, we are using both the the field data as well as the data from the previous the data generator. So here is the workflow of the maintenance predictor with the sample generator. So I won't go into details for this one for the interest of time. And here presents some results. We're using different optimizer to look at the which one is the best with the best performance. And from this this failure time comparison, we can see the accuracy of the prediction model is acceptable. So from this this work actually it provides a practical paradigm for the system operator or practitioner working with the daily equipment maintenance application. The advantage of this combination of model-based and data-driven approaches, it helps it helps the system operator to dispel their misgiving at the uninterpretable pure data-driven approach. So by introducing this proactive maintenance, we can solve the data deficiency problem, and also to have a deep understanding on the physical failure of the power equipment. And so this is the first application I would like to introduce. So the second one actually relates to the security of the power system. So I just mentioned there are three aspects, right? So the first one is reliability. The second one we actually we look at the security of the power grid. So we developed a concept of a tool of the situation awareness of the power grid. So recently, the power grid actually experienced more and more threats from the power electronics based resources connect to the grid. So for the new power electronics based renewable generation, right? It greatly reduced the system inertia, and also due to the the characteristics of the for example like a wind or solar, it introduced a massive system uncertainties. It changed the system dynamics a lot. So in this connection, it's significantly jeopardized the security of the power system. The conventional dynamic security assessment has been used for a long time, but recently we have experienced more and more cases. It fails in predicting system insecurity in the real-time environment, and leads to severe consequences. So one famous example is the UK blackout in August 2019, right? So for this event, actually, it is due to the simultaneous reduction of different types of generation, right, in the UK system. So we have seen the loss of the thermal power plant, the wind farm, as well as some embedded generation connect to the distribution grid, right? Although the conventional the DSA can secure N-1, right? The insecurity, but for this case, it fails in predicting the system's insecurity for this blackout. And sometimes even you have the technique, but you don't have enough data. For example, for these ones, the insecurity has actually happened in different levels of the power grids, including the transmission, right? The sub-transmission of the wind farm, right? As well as the distribution. So for system operator, it's difficult to actually collect all the data, and I mean the model, and to carry out the security analysis. So that's why we want to develop a tool to not to replace, maybe in the future to replace, but at the moment to compensate, right, the insufficiency of the DSA in order to help improve the system security. So this situational awareness, this concept is actually, it refers to the perception of environmental elements and events with respect to time or space. It is the comprehension of the the system status and the projection of their future status. Right? And this concept was firstly introduced by the U.S. Air Force in last century, around 1980s and 1990s. And recently it was introduced to the power system power grid. So so why we need the the deep learning based situation awareness? There's a concept, there's a context about the cyber physical system. So as you may know, in 2015, the Ukraine experienced a blackout, and this blackout actually is due to the cyber attack, right? So, and from that time, onward, the cyber security become a very hot topic, right? In the power system, security, studies, and in around last year, right? The U.S. government passed legislation to isolate the power equipment from the grid operator due to control system to prevent similar blackout accident. So this is probably the first well-known, the legislation document, right, in the world to actually emphasize the need of the study on the cybersecurity issue when we're doing the power system security analysis. So you can see there are quite many types of data corruptions, right, in the power grid when we are doing the situation awareness. So the conventional situation awareness is not very good at tackling the data corruptions. So that's why we introduced this the deep learning based situation awareness to tackle this data corruption problems. So now let's look at our solution. We are using an enhanced situation awareness based on the random matrix and the deep learning techniques. So the random matrix was not invented by us, but we just try to to borrow the concept, and for this random matrix, it will generate an index called the mean spectral radius, the MSR index. And for this MSR index, it can tackle or kind of immune from the impact of data corruptions, but it makes the situation awareness detection not very sensitive as well. The extreme case is the anomaly is quite similar to the data corruption, so you cannot really differentiate, distinguish, these two. So that's why we introduced this, the deep learning techniques. Specifically, we're using the long short-term memory recurrent neural network. So to predict the previously mentioned the index MSR. So we proposed a new index called the GCSE, the gradient of the cumulative square error. So this index is trying to compare the real MSR with the predicted MSR. So based on this comparison, we can actually identify if this is a genuine anomaly in the system, or it is holding a data issue. Okay, so this GCSE indicator is designed to compare, as I said, the predicted MSR by the LSTM and the true MSR value to magnify the quantitative distance between the predictive and the true MSR. So it can help detect the genuine issues in a very sensitive manner. So we use the New England test system and the New York power system to validate this situation awareness tool. The red dot in this diagram represent the PMU. So you might wonder why we have so many PMU here. So, but this is just the initial, validation. Later, we also actually test different numbers of PMU and their performance. Okay, for this these techniques. So here, maybe I just have a quick, introduction on the random matrix as well as the MSR, the theory. So you can see, actually there are, three circles here, right? So basically, the blue dashed circle and the green, kind of dashed circle, they define the upper and the lower bound of the the system operation margin. Okay, so the red the red circle actually is like a indicative circle, which represent the distribution of the eigenvalues, okay, of the system, from the random matrix. So you can see, in a steady state, so when the system is secure and stable, this red circle should be, between the blue and the green circle. So which means the system is in a secure manner. But when the anomaly or system fault happen, so the eigenvalue will will come to the middle, okay, of the blue circle. And after the fault or after the anomaly, if the system can return to a steady state or stable or sustainable status, the red circle will come back, okay, to the original phase. But if the system just become unstable or insecure, the red circle will be just in the middle. It won't go back to the origin place. So that's the brief idea about the MSR. So you can also see this this comparison and diagram on the true MSR value and the predicted MSR value. So based on the comparison, we can plot the proposed index GCSE. Right. So we have tried to set up different data corruptions, for example, like data loss, time delay, and also we also validated the cyber attack, one type of cyber attack called the replay attack in this example. So we apply this data corruptions to different PMUs. Okay, and also we design different system anomaly, for example, like earth fault, a wind farm offline to disconnect the wind farm, as well as load loss. Okay. So you can see the different, the change of the GCSE, right? In this case, and also we designed the the step variation of the wind power output. So this is like the fluctuation, right? And also the wind farm switching, right? So you can see. So after the wind farm switching, there are actually actually result in the system's insecurity, and you can see the change of the GCSE. So, and we also look at the small disturbance awareness under the data attacks. So, and to see if the system is, small disturbance stable or not. We also look at different numbers of PMU, the impact of different numbers of PMU on the performance of the analysis. And from this performance and the chart, you can see for the original initial condition, we have 38 PMUs right, in the system, and then we try to reduce it to 65432 PMUs. You can see from this chart around 5 PMUs or 4 PMUs. The tool can still provide comparatively accurate results. Okay. So it means this the tool is quite effective and practical. And we also look at the secure status on the typical scenarios of person with different wind power penetration levels. And we look at different events, for example, like the wind fluctuation to connect the wind farm to the grid, and some different types of sequential contingencies and small disturbance, and we analyze the system security status. Okay, so this is a so-called enhanced situational awareness tool we developed. So for the situational awareness concept, when it first proposed, actually it proposed with 3 levels or 3 different levels of concept. The first one is called perception. For example, if you detect some anomaly in the system, it is in the perception stage. The second stage is called comprehension. So the comprehension means, on top of the perception, right? You have some deep understanding, okay, on the system status. So this is comprehension. The third stage is the projection, or so-called prediction stage. So this is a more advanced stage, but it's very challenging to achieve. So for this study, we look at the situation awareness of the person security toward the prediction level. So for most of the situation awareness prediction studies, we found the Olin focus on mining from either temporal, which means time, or spatial perspective. There's a very few study it utilizes both of them simultaneously. Simultaneously. Yeah. So this work actually is a collaborative spatial temporal analysis on the system status data. So we are using the deep learning techniques, specifically the CNSTM model, to predict 2 major index. The first one is the location of the fault of the system anomaly. Okay. The second one is to predict system stability security margin. Okay, to see if system gonna be stable or unstable. So with this 2 indicator, we can give the system operator a heads up. Okay, So they can, further, process. So for example, they can clear the fault or carry out the operational interchip or deload the generation or switch line, right? Based on the indicators from these techniques. So due to the time constraint, I'm not going to the details, on the deep learning, but you can refer to the paper below, okay, for more details. So we are using multiple layers of CNN, right, for the model training. So now let's look at the test result for this prediction level of situation awareness tool. So we are using the New England test system and the New York pass system as a benchmark system to test the tool. The red dots still represent the location of the PMU. Okay. So later we will actually look at a different deployment style and location of PMU and its impact on the effectiveness of the tool. We're trying to minimize the loss function of the prediction model. So if you look at the prediction accuracy in this table, so I think the worst result of the case is around 95%. Okay, so no matter for the predictor accuracy of the locator accuracy, they are above 95%. So we regard this as quite satisfactory. And also we compare this CNSTM with some other deep learning and machine learning techniques, for example, like the STM, MLP, RF, and SVM, right? And we found out this CNSTM techniques are with the highest prediction accuracy, and also the test time is comparatively short. Okay, so I should say the performance is quite good. So we also look at to reduce the number of the PMU, like the previous case, and also we look at different prediction time, right, after fault. So as it's quite obvious, right? If we have a longer prediction time, which means from the fault to the time point you predict or you provide the prediction result. So the longer the time is, the more accurate, right, the result will be. But the longer the time it takes, right, it means you have a shorter time given to the system operator to do the post-fault action, right? So even you let the system operator know the system is unstable, right? If they don't have sufficient time to action, right, to act, so it won't make a big significance or difference. So we need to strike a balance between the prediction time and prediction accuracy. So here we try to test the extreme condition, and we found out to have a better accuracy, for example, 90% of accuracy, we need at least have 11 PMUs deployed in the system, and the prediction time should be no less than 0.4 second, okay, after fault. So, but you can kind of imagine, the 0.4 second is still, quite short, period, right? So I should say these kind of the condition is still quite, satisfactory to us. And apart from this, we also look at the different Pmu deployment patterns, which is not, demonstrated here, but we look at, for example, the centralized deployment of Pmu or, distributed deployment of Pmu, right? We look at different, styles, and we found out the distributed, deployment of Pmu actually has a better performance than the centralized. But the centralized is still, with satisfactory results. And also we look at the different types of conditions. For example, like three-phase fault, single-phase fault, right, unbalanced fault, and some other contingencies. And the development tool can, effectively and efficiently identify the location of different types of conditions. Okay, so this is, the situation awareness, techniques, for the prediction level. Okay, I'd like to demonstrate here. Okay, so now let's move to the security aspect for another, area, which is on the low voltage system. So we actually look at both the active distribution network as well as the microgrid. But this, concept is based on the so-called distributed control, okay, of the network. So before I introduce more details, I want to have a quick brief on the the control structure of the power system. So normally we have the control in the classification. We can have the so-called centralized control, decentralized control, and the distributed control, right? So for the centralized control, it relies on a powerful hub, to collect the global information of all components in the system, and so that it can conduct the computational procedure. And due to the ever-growing penetration level and the distributed nature of distributed energy resources, the centralized strategy are going to encounter some technical challenges. For example, it will have a heavy computational burden and communication complexity, right? So this is the first challenge. The second challenge is it is susceptible to the single point failure, right? So if you have a single point failure, it might affect the whole system, right? The third one is it is unable to accommodate the plug and play, function of the DER, right? So in this context, the fully distributed strategy are preferred for their superiority of the scalability, sparse network, and the improved resiliency, to faults or unknown parameters. So that is why, for the low voltage, system, it kind of borrowed the concept from the conventional, transmission system, to apply this distributed control with in a hierarchical, manner. So as you may know, for the conventional frequency, control or regulation of the transmission system, it consists of 3 different control layers, right? And the primary control, the secondary control, and the tertiary control, right? So for the first 2, they are automatic control, but in different time scale, right? The primary control actually is talking about the response from the the governor, right, system. And after the action of the governance system, the system might experience the the steady state deviation of the frequency, right? So that's why we introduced the second control to utilize the automatic generation control, right? To remove or eliminate the steady state deviation of the frequency. And for tertiary control, it's more related to the kind of the different contract, right? Different contract of a reserve. So this is the conventional frequency regulation concept with the 3 different layers. And for the low voltage system controls, we are kind of borrowing this concept. So for the primary control, normally it's used the droop control. Okay. In the old days, we used the master-slave control, but it was an old design. It highly depends on the master node or agent. So that's why it is less flexible and reliable, right? So if you have an outage, no matter it's unexpected or expected outage, so it will affect the whole system, right? And also it suffers from the single point failure, as I just explained. So if we apply the droop control for the low voltage network, there should be also a deviation, right? It's just like the frequency deviation of the conventional transmission system. So that's why we need to have this secondary control in order to minimize this deviation. And also for this second control, we could introduce some economic factor, right? To consider some economic factor. For the tertiary control, it's normally used for example, like economic dispatch, cost optimization, or some market-oriented optimization. Okay, so this is the use of a tertiary control. If you don't consider the market factors or some like unit comment or economic dispatch factors, right? You could remove the tertiary control, right? You could just have the secondary control and a primary control. And for the time scale of the low voltage system control are quite different from the the conventional frequency regulation controls. So normally for the primary control and secondary, they are nearly real time. They're real time control. For tertiary control, it could be executed every 5 to 10 or 15 minutes. Okay. So in terms of the time scale, is with comparatively short time scale compared with the conventional frequency regulation. So for the active distribution network, we need to have some hardware support in order to achieve distributed control. So from the this diagram, okay, illustrated diagram, you can see there are quite a few DERs connect to the distribution network, like the wind integration, the PV, right, and the EV, right. So that's why we call it the active distribution network, because there are massive, more and more the active power sources connect to the distribution level of grid. And recently we also have the advanced communication infrastructure development in the active distribution network, which facilitate our control strategy. And also for most of these DRs, they are connected via the power electronics interface. So which means they are more controllable. Okay, so they are more flexible and controllable for the efficient ancillary service. So here I just use the EV charger as an example, to kind of to demonstrate the operational mechanism of the power electronics converter. Okay, so for each, the interface of the power electronic converter, it should have some, limitation on its active power and the reactive power. Okay, so this is like the four quadrants output of the P and Q. Although they have a kind of a limit, right? But they are fully controllable. And in this study, we also use this so-called intelligent bus terminal. So for this IBT, it consists of physical advanced IoT devices. It equipped with three major functions, namely monitoring, computing, and communication. So it can be, predict for sure in the future with the development of 5G technology, as well as the edge computing, or so-called fog computing technology. So this all of this technology will further facilitate the implementation of the distributed control of the low voltage network. Okay. So one of the the typical characteristics of the low voltage network is the RX ratio is different, right? It has a high RX ratio. So when we try to do the ancillary service or to regulate the voltage or frequency, we need to analyze the impact of RX ratio, right? Because you need to know how effective it is to adjust the P or Q in order to to regulate the voltage or frequency, right? So in the conventional grid, we think the active power and the reactive power is decoupled, right? Because the RX ratio is very small. So we can treat the we can use the reactive power to regulate the voltage in the conventional grid. But in the distribution network or in the microgrid, we find out actually sometimes P is more effective. It's more effective in regulating voltage, and sometimes Q is more effective in regulating frequency. And also, we found out the conventional Jacobian matrix, which is used for the sensitivity analysis of the QV, right, curve. In this application is inaccurate. So the conventional Jacobian matrix requires a global information collection and cannot handle many nonlinear elements like different smart loads. So so in this study, we used a very simple topology system in order to kind of analyze the impact of our RX ratio on the voltage regulation. Okay. So we have some assumptions, like we assume the small voltage angle theta, right? So we can derive this very straightforward, right? Simple relationship between the voltage, which is the receiving end voltage, and sending end voltage, E. Okay. And one interesting conclusion we find here is the sensitivity. Okay, the sensitivity of the P and Q. Okay, with respect to voltage, actually their ratio is equal to the RX ratio. Okay, so which means if you have a higher RX ratio, it means the P is more effective in regulating the voltage. So this is quite obvious, right? So we just mentioned the conventional Jacobian matrix is not that accurate and effective in analyzing the sensitivity, right? Voltage regulation. So that's why we introduced this perturbation approach. It can be based on simulation, or it can be based on the real time measurement. So we use this IEEE 13 bus distribution network to further validate different Rx ratio and their impact on the P and Q effectiveness. So from this case, you can see when Rx ratio is equal to 1.34, you can see the P. The P injection is more effective, right, than the Q in order to change the busbar voltage. Here we'll look at the most vulnerable bus, which is bus number 13, and this one is could be the most the remote end of this of this radio distribution network. And based on the appearance mentioned in the hardware and also the the Rx ratio analysis, the sensitivity analysis, we proposed this 3-layer, 4-layer distributed control. So we can start from this normal scenario, which is when communication network is in service. So when communication network is in service, we can actually share the information. We don't need to have a global sharing of the information. But here, what I mean to share the information is just to share the information with different neighbor node. Okay, so that's why it's called the distributed control. So what kind of information we need to share? So firstly is the kind of the willingness, the involvement level of the EV, of the EV, or in other words, it actually indicates how much power P and Q the EV can provide in order to regulate the voltage. Okay, so what the the EV user need to provide is the their trip planning, like how what kind of the destination they plan to go, as well as the current SOC, okay, of the EV. So based on this two information, two types of information, we can compute this the involvement level or the PQ, which the EV can provide. And the other information we would like to share within the neighborhood is the demand, or is the how much P or Q is needed in order to regulate the voltage. So here actually we are using the measurement data in order to compute the sensitivity, right, and to compute the required P and Q. So by using the communication, we can and also the consensus algorithm, we can let all the system nodes know how much power P and Q they need to provide in order to regulate the voltage of the critical bus. So this is during the normal scenario. So in emergent scenario, when the communication network is out of service, okay. So in this case, the the three-layer, right? The three-layer, communication control strategy degrade, okay, to a single layer. So we only have this control layer. But in this case, we proposed dedicated support from the local, energy storage system. So we use the battery or some, like the fuel cell, right, to provide the voltage support to the critical bus. So that's the design. So here are some details about different layers. For the interest of time, I won't go to details. So here is the test result, okay, for this, the voltage regulation, distributed control. So we first, test this in a, a simple distribution network, okay. So you can see the communication actually is quite simple as well, okay, for this case. So we intentionally designed a three load sharp change, right? So to see if the algorithm can achieve the convergence, right, in a timely manner. So it can be seen that by using the average consensus algorithm, so most of the time the technique can achieve the convergence around 20 to 30 iterations. The reason we did not present the time, but using the iteration here is you might have different computer to processor, right? So if you have a high capability processor, right, it might be much faster, right, than some normal processor. So that's why we are only look at the iteration. And we also look at different like the PV variation or random load change during the communication failure. We tested the second scenario without the communication. So for all the cases, the results actually are quite satisfactory. Okay, so we just talk about the voltage regulation. So the second one, we look at the frequency regulation of the distributed network. So like the person mentioned in a three-layer hierarchical control. So here we propose three-layer as well. For the primary layer, it is the we use a tube control. And for the secondary generation regulation, we are using some consensus algorithm, okay, to achieve the distributed control. And for the tertiary, we're using the ADMM plus the discrete consensus algorithm in order to achieve the fully distributed, as well as the most cost-effective solution. And here are some details. I won't go into the details. So if you have interest, you could refer to the paper. So now let's look at the simulation results. So here's the modified Iai 33 bus test system. So you can see on this system we have installed some DERs, smart loads, and storage, and wind farms. And for the tertiary control cycle, we set up at 300 seconds, which means 5 minutes. Okay, and we also have some system event setup, like we have some load change or load forecasting deviation, as well as the DER11, plug in and plug out. And for the communication, we're using or we are proposed to use the wireless communication for this network, or in the future it could be the 5G. Okay, and we're trying to prove the proposed technique is robust to communication errors and time delay. So the extreme case is the disconnection or and the disconnection of the communication, right? So the hierarchical layer, 3 layers of control will degrade to the primary frequency regulation layer only. So here's the comparison between the proposed discrete finite consensus algorithm with the conventional the consensus algorithm. The difference is the finite consensus algorithm, it can actually converge with a certain iteration. For example, you set up at 40, so there's a very strict theoretical proof that the consensus algorithm can be converged within certain step. So this is the validation of the consensus algorithm. And also we look at the effectiveness of the ADMF on the tertiary layer. All right, so you can see, although it is a distributed organization, but in terms of the result, it is very close to the centralized economic dispatch result, right? So, and we also look at different control sources, to be utilized. For example, energy storage and controllable load, right? We look at different control layers and strategies. So this one actually is mainly refers to the the different communication, right? Different communication status. You can see at the bottom, the blue curve is the one without communication, right? So this is the worst case. So, but even with the worst case, the frequency deviation is within 0.5 hertz, so it is comparatively acceptable for us. Okay, so next one I would like to talk about the microgrid, secure operation. So for the microgrid, it is quite similar to the distributed network, but maybe it is it's more it's simpler, and also it's more flexible. So normally in microgrid we have some inverter-based equipment like DJs or energy storage or load, and the microgrid can be grid connected or can be islanded, right, in terms of operation mode. And for the the microgrid control, actually is similar to the concept I mentioned previously. It can be classified into 3 different categories: the centralized, decentralized, and the distributed, right? So as I mentioned, the centralized controller, right? They try to optimize the operation and control of the overall microgrid with global decision making. And the disadvantage of this is the high dependence on the centralized controller. And that's why it is with a low reliability and scalability. And it's difficult to meet the plug and play requirements, and it's difficult to meet the confidentiality of information between different operators. The decentralized control in the middle, the advantage is there's no need for communication with decentralized one. It can adapt to the plug and play operation with a high reliability. But the disadvantage is it is difficult to make the globally optimized decision. So you cannot use the decentralized to make the globally optimized decision due to lack of effective global information across the wide system. The local decision making may challenge system stability as a resulting the interaction between the different distributed generations. So that's why we prefer still the distributed control in this case. It is using the sparse communication network and the local neighboring information to obtain the quasi-global information and then to achieve distributed local decision making. The key features of this control is it is with a partial information exchange between neighbors. The communication topology is sparse. You don't have a very complete communication topology. So later I will actually we will look at different communication planning. And also it is a distributed local decision making, but it can achieve a global organization. So different from the consensus algorithm. So here we used a so-called opinion control. So the advantage of opinion control compared with the consensus algorithm is, firstly, it can set up a reference like a target. So previously for consensus algorithm, when we try to regulate whether frequency or voltage, right? We're trying to make the voltage right to within certain range, but not to be close to the, for example, like a nominal or target. But for opinion control, you can have a reference, a target, to actually follow. Since it has a reference, right? It could be more effective for the opinion control. So you can have less agent or less system nodes to be controlled. So that's why the opinion control actually it can enhance the control performance and simplify the control structure and resource. So here it presents a basic a structure for the primary control and the second control with the pinning the secondary control protocols. So here I present the details about the pinning control. Okay. So for the pinning control, we mainly look at how effective it is to actually reduce the communication cost, right? But on the other hand, we need to make sure the control is effectiveness, right? To see if it converge or not, and also to look at the controller stability. So that's why we use the graph theory to look at the communication planning problem. So here we introduced a matrix called adjacency matrix A. So this matrix actually is purely based on your communication topology. So for the communication topology, you can actually have one direction or bi-direction communication. So for this example, we have a one direction communication. That's why we have the A matrix like this. And based on this A matrix, we can further derive a so-called degree matrix D, okay, of the graph. So this degree matrix is a diagonal matrix with the ith diagonal entry as the out degree of the ith node. So this one actually is based on the matrix A. And based on these two matrices, we can derive a so-called Laplacian matrix of the graph. So by calculating the eigenvalues of this Laplacian matrix, it can indicate, the performance of the network dynamics. So basically, we are looking at the second largest of the eigenvalue of this Laplacian matrix. So here are some, a very rigorous and strict, theoretical proof on the theory we proposed here. So I won't go into details. And based on this, we can, plan the communication network of the microgrid in order to achieve the distributed, painting control. So previously I mentioned, for this A matrix, right? If you have, for example, if you have a distributed DG1 connect to the DG4 in terms of the communication, right? So you can have this, this element, right, in a proper, location equal to 1. But it is not necessary it is only, equal to 1. You can actually apply different weights, right, to different communication. For example, if you treat this, communication between DG1 and DG4, right, as an important communication channel, right, you can, probably put 2 or 3 here as a weight. So actually, the cost function for communication is just, to the sum, to sum all the components of the A matrix. So when we look at this optimization, problem, right, we need to make sure the dynamic performance of the communication and the control, and also the controller stability. We found out this optimization problem is it's like a non-convex problem. So that's why we need to have some relaxation using the linear matrix inequalities and the KKT conditions, right, to relax the problem to solve the this optimization formulation. And here is a simple case study, right, to test the performance of the painting control based distributed control of the microgrid. You can see no matter for the frequency or for the voltage, it can achieve the target. And also we look at more complex system. Okay, so for this case we have 8 DG microgrid. We look at a different control communication topologies. So you can have different design, and they are with different costs. So and we try to optimize the communication topology to see which one is more effective. Okay. So the last one we look at the economic frequency regulation strategy for the scattered microgrid. So previously, mentioned the microgrid, they are very, simple, right? They're just like a single microgrid. You might wonder, for a complex microgrid, how can we apply the, frequency regulation or voltage regulation? So here we just, present an example, on the economic frequency regulation, but it could be applied to the voltage regulation as well. So we try to kind of distribute it, okay, the microgrid, or to separate the microgrid to different small so-called nanogrid. Sometimes it's called a network microgrid. Okay, so in this case, so for each nanogrid, it could be like a community network, or it could be a building, even like a building. It could be a nanogrid, right? So for each nanogrid, right, they should have their own a regulation system. But between the nanogrid, we can have a very simple communication network, right, design in order to to achieve the communication function. So that's why we proposed this two-level control strategy. So the upper level is on the nanogrid level, the lower level is on the DER level. So the both level, they will achieve the distributed control. For the nanogrid, it is using the discrete consensus algorithm, okay, in order to minimize the the incremental cost. And for the DER level, we're using the pinning control, pinning protocol for the secondary frequency control. So here are the test results, okay, for this two dual level distributed control based on the pinning control protocol. You can see actually each nanogrid can provide, right, actively provide the answer service frequency regulation to the whole microgrid, right, in a cost-effective way. And the tracking performance is quite satisfactory. Okay, so for more detail, you can refer to this conference paper listed below. Okay, so due to the time constraint, my presentation will be ended here. So we have actually more to present if in future if there's a chance. So so thank you for your listening, and your questions are very welcome. Thank you.
Thank you, sir, for your detailed session on intelligent operation of modern power systems. This is one of the most sought after areas in power systems in which application of machine learning is well fitted. The importance of predictive maintenance of power equipment and enhanced situational awareness for event detection and preventive control were clearly delivered. The secure operation of active distribution system and microgrid was also discussed. The session is now open for discussion. I would now read out some of the queries posted by the participants. First query is, how do we select the number of hidden layer neurons for the ANN, and how do we choose an activation function in ANN?
Yeah, I think this is a very good question related to the to application of the deep learning. Actually, in our study, we didn't optimize like the numbers of the hidden layer neurons. We just used a very a normal and regular AN to study the problem, and we found out actually the result is quite satisfactory. So that's why we didn't look at how many layers. I mean the numbers is the optimal numbers. So yeah, so actually we didn't actually look at this issue, but maybe in the future we can have a look at to achieve a better, even better result. Yeah, so that's my answer.
Okay, thank you, sir. Next is regarding what does a random matrix represent?
Okay, yeah. As I previously mentioned, the random matrix is actually, let me quickly go back to this slide. Yeah. So actually, the random matrix is like a matrix. Actually, consists of the data environment. Okay, so basically, it is a matrix of data environment. So the theory here is we try to look at the characteristic, the features of the data measurement by using the random matrix theory. So we look at the eigenvalue, and also the shape of the eigenvalue, which form the mean spectral radius, which is called MSR here. So so if you ask the random matrix represent what they represent, there's no kind of the physical, there's no physical meaning of a random matrix. But what I would like to demonstrate here is, or explain here is, it is a very good tool actually to analyze your data measurement, and also to deal with your data corruption. Yeah, it is actually a very good tool to filter out some noise or some errors of the data measurement. So yeah, that's my answer.
Thank you, sir. And the next one is, how does one determine the optimal location and number of PMUs?
So yeah, actually it's by we don't have a like a optimization formulation. What we do is we try to enumerate different combinations or different the deployment strategy of the PMU. So we're trying to find which is the best, or how extreme condition we can go to. So I think because this not the focus of this the development tool or techniques, but I think this is a very practical factor we need to consider for the real implementation. So that's why we didn't introduce any optimizer to optimize the PMU numbers and the locations. Yeah, we think we regard this as another issue, maybe to be studied in the future. But at the moment, we think with all the enumerate conditions, we can achieve a satisfactory result.
Okay, thank you, sir. Next query is, power system means a large network. It means many buses and many variables to control or observe. For many number of variables, how will we make training practically? Also, how will we determine weights for these variables?
Sorry, can you repeat? I didn't quite get it. Yeah.
Yes, sir. Power system means a large network. It means many buses and many variables to control or observe. For many number of variables, how will we make training practically? Also, how will we determine weights for these variables?
Yeah, that's a very good question. Actually, we are more concerned, about the opposite direction, not this one. If you have more measurement and more data, right? You might have the processing or computational burden or communication burden. Yeah, that's true. But I think at this stage, or I mean, practically at the moment, we're more actually concerned about lack of data, not just too many data to be processed. But I think in the future, that could be a challenge for us. I mean, to look at. So you should know a concept that the quantity of the data, right? It doesn't mean the usefulness of the data, right? So even you have millions of data, right? It doesn't mean the millions of data are all useful. So I think the first step is to screen, to see really to different tasks. For example, like dynamic security, right, and assessment, or specifically like a transient stability and analysis, right, prediction. You need to kind of select the data you want are really useful to you, right? So that's the the first step. The second thing is second thing is we need to actually strengthen or reinforce our communication and the data processing capability. Actually, this should be quite promising because with the the edge computing technology, or fog computing, actually we can very efficiently and and also cost-effective, okay, in a cost-effective way to process the data in the edge. You don't need to even to communicate or to transmit the data to the to your control center or to the processor center. So, and also in terms of communication, we can use the wireless or with the development of 5G, right? In the future, we have more the capability, right? Higher capability of communication in terms of transmit data. So I think it is a challenge, right? For a big system, right, to get a lot of data and to process. But I think we need to use the data, wisely, and I believe in the future we have the capability, we have the competence to process and to transmit the data. Yeah, with all the infrastructure being reinforced. Yeah, thank you.
Thank you, sir. And one last query: how to differentiate nanogrid and microgrid with respect to voltage and power ratings?
Yeah, actually, it's a very good question. A lot of people ask. So there's no actually a fixed or a well-known definition about the nanogrid and the microgrid. So in many circumstances or many cases, you don't see nanogrid. Maybe you see like a network microgrid, right? So it just different people have different use different terms. Yeah. So but we think for the nanogrid and the microgrid, I think in the future there'll be there will be a proliferation of the nanogrid, kind of layer of microgrid. So so we need to sort of try to control and regulate the voltage and the frequency on the nanogrid level in order to achieve a global optimization on the microgrid level. So that's why we proposed this kind of a generic paradigm, try to solve the whole microgrid regulation or answer service issue on the nanogrid level. Okay. But it doesn't mean like we don't have communication between different nanogrid. We need to have communication, but that communication is very limited. Actually, we have some other studies or research regarding the peer-to-peer trading. Okay, but that one actually is focusing on a different time scale, a longer time scale. So we are using the resources in the nanogrid in order to achieve the microgrid regulation target. So for the nanogrid with abundant resource, for example, there's a lot of EV, right? It could be a real-time changing condition, but the nanogrid with more EV charger or with a more smarter load or controllable load, it can provide more ancillary service to the microgrid. So it can be it can have more profit if it has more capability. But in general, generally speaking, if we can achieve a nanogrid security and stability, right? The whole microgrid will be stable and secure. So yeah, so that's kind of the concept and the mechanism we try to use and achieve.
Okay. Thank you, sir, and the participants for making the session interactive. I would like to especially thank Dr. Siqi for his constant support and motivation through the planning and execution phase of this workshop. Once again, thanks for your involvement, sir. I would also like to thank our eminent speakers who have joined this session, especially Professor Shanti Swarup, Dr. P. Raja, and Dr. M.P. Selvan.
Yeah, no problem. Thank you very much. And if you have any further question, you're welcome to contact me via email. Okay, so we can have further discussion. Thank you.
Okay. Thank you, sir.
Thank you very much for being with us, sir. Thank you very much.
My great pleasure.
Yeah.
Thank you. Have
yes.
a nice day.
Thank you. Yeah. Thank you, sir.
Now regarding the next session, we will join back at 2:30 p.m. today for the talk on solar PV potential estimation by Dr. Rhythm Singh, Assistant Professor, IIT Roorkee. Please join with the same link. Thank you all for joining the session.